So 19.3 has to do with strong and weak acids and bases. So we've already talked about concentrated versus dilute, and now we're going to use the phrases strong and weak. They are different. Okay, so let's define strong and weak first, and then we'll compare them to dilute and concentrated. So acids and bases are classified based on the degree to which they ionize in water. Oh my gosh, let's dissect what that means. Remember we said that ionize means that they break apart into ions. Okay? So strong acids and bases completely break apart. That means all of them break apart into all of their ions. And so that can be called ionized 100%. So that means every single sulfuric acid molecule breaks apart into a hydrogen ion, and then the rest. Okay? But not all acids are strong. Not all bases are strong. If they are not strong, they are classified as weak. That means they ionize only slightly. So not every single acid molecule breaks apart. Only some of them do. And so that's considered a weak acid or a weak base. So that is different than concentration. So something can be concentrated, like 12 molar, that means it's really concentrated, but it might not be strong. It might, even though it's very concentrated, it has lots of molarity, it might not completely ionize. Okay, so strength is very different than concentration. Okay, so strong means it ionizes 100%. Each and every molecule of that acid or base breaks apart into ions. That's what strong means. We can have strong acids and strong bases. I'm not going to make you memorize, but they're really not that many. And again, there's going to be some that just kind of come up a lot, and you'll be like, oh yeah, that's a strong base, or oh yeah, that's a strong acid, just based on going through them. Okay, so this shows what happens when you have a strong acid, HA, that's just a generic acid, and so when it completely disassociates or completely ionizes, that means every single HA molecule that you started with is going to break apart into two ions, an A and then an H+, and that H+ is going to jump onto the water, so that's why it's shown there. And so the only reason I'm showing you this graph is to realize that every single one of those acid molecules is going to break apart. And just like a water breaks apart into two pieces, if we're talking about an acid that's strong, every single acid molecule is going to break apart into two pieces. And we would expect that those two concentrations are going to be equal. See how the red and the blue bar graph are the same height? That's because it's made that same number of ions when it breaks apart. And same height as the HA2, you're exactly right. Now, this is a graph of a weak acid. So only part of those acid molecules are breaking apart. So you see your initial concentration of HA, and then some of those HA molecules break apart into A- and then the H3O+, but not all of them. And then you see some of them, more of them, stay together as an acid.
What is HA?
HA is just a generic form for acid. So the A stands for acid. This could be hydrochloric acid, sulfuric acid, nitric acid. It's just in general. Okay, good question. So how are we going to measure this? Because of course we got to measure it. Got to measure everything. Okay? What? All right, so we are going to measure this by something called an acid dissociation constant. Ka, let's call it Ka, shall we? It means how much of those acid molecules are ionizing, how much of them are breaking apart. And we can measure this. And this number will give us an idea how strong or weak the acid is. So a high number for Ka would be a strong acid. And a lower number for Ka would be a weaker acid. Let's see if that's on here. Oh, yes. It is. Oh, sorry. So a higher Ka is going to be a stronger acid because more of those acid molecules have dissociated. So let's kind of break apart that equation. So Ka is going to be a value, that we're going to calculate. The H plus and the A minus, again, A is just kind of our generic term for acids. So H plus and A minus, now those are going to be the same, okay? Because when one acid molecule breaks apart, we get one hydrogen molecule and then the rest, and that's what's signified as A minus. So even though it's written like this, usually you're just going to have the H plus and you're going to square it because they should be equal. Okay, when one acid molecule breaks apart, it breaks into two pieces, the hydrogen and then what's left. Okay, now your book makes a really confusing chart out of this, and I'm going to encourage you to not look at it because it's terrifying. Okay, so and then the concentration that you've started with at the bottom, and usually that's in a molarity, so you'll be comfortable with that number. But those H pluses are usually teeny baby numbers, so don't forget to use your parentheses. And don't forget to make sure your exponent is the right way, and they're little tiny numbers. So sometimes you get little tiny numbers. That's okay. That happens.
Wait, what is HA?
HA is your initial concentration of the acid. Good question. Okay, we're going to work with Ka first, but there is also a Kb. That is the base dissociation constant. Looks very, very similar, except this time we're working with a base. Again, the M is just for metal. This is a generic term for base. We know a base is a metal and then a hydroxide. So the MOH on the bottom is your original concentration of the base. And then again, there are two pieces that come apart. You'll probably be given the OH concentration, and then you're just going to square that because those two, the M plus and the OH minus, should be equal to each other because when a base dissociates, it breaks into two pieces. Okay, same thing here. The stronger the base, the larger the Kb value is going to be. More ions are dissociated, more bases have broke apart, base molecules I should say, and so you would expect a stronger base to have a higher Kb. Here's where rounding is going to cost you the answer. I know I've been lenient on rounding, but if you are rounding here, you are going to get the wrong answer, especially on those teeny baby numbers. So you already have this in your notes from back before when we talked about solutions. Concentrated and dilute talks about how much of the acid or base is dissolved in a solution. That means how, like the molarity. So the higher the molarity, the more concentrated it is. But strong and weak refers to how much ionization is happening. When we mix the acid and base with water, how many of those molecules are actually breaking apart into ions. So those four words are not interchangeable. And concentrated is not interchangeable with strong, and dilute is not interchangeable with weak. They mean different things. You can absolutely have a concentrated weak acid. Absolutely. That is possible. Okay, so let's practice. If I give you this equation, usually it's just going to be an acid. Maybe it'll be plus water, but maybe not. And it just talks about that acid breaking apart into ions. And this just asks for you to write the expression. It doesn't actually give you numbers. So your Ka would have your initial concentration of the acid on the bottom. That's what those brackets are for. And then the H plus and the NO2 minus on the top. If I were to give you numbers with this, your initial concentration would go on the bottom. Let's say it was 0.5 molar. Okay, that would go on the bottom. And then you know your H plus values have been teeny tiny, like 1 times 10 to the negative third. So if I give you that that is the value for H plus, I would just square that on the top. 1 times 10 to the negative third, and then I would just close my parentheses and square it. Because for every HNO2 that breaks apart, there's one H and then one NO2 minus. So they should have equal concentrations. Now this is where your book likes to make it a little chart. I really don't think that that's necessary. So on this picture, I don't want you to freak out at this chart on the bottom. Do not freak out at the chart. This is on page 610 if you want to take a closer look. And so it gives us the original concentration of the acid, and it says it's only partially ionized, and then it gives you the H+ concentration, and it asks you to find the Ka. So your 0.1 molar is going to go on the bottom, and then your H+ gets plugged in. But I am going to assume that the H+ concentration and then that other concentration, CHCOO-, are equal to each other. So I'm just going to take the 1 times 1.34 times 10 to the negative third and square it. I would actually do that first and then divide it by 0.1, and that should give you your Ka. Again, I don't want you to freak out about the chart. I want you to close your eyes and not even look at it, because the book makes this more complicated than it needs to be. And that's your answer. And your answer doesn't even have a unit. It's just the number.
Heck yes.
Woohoo!
That's the least thing I'm worried about.
It's the least thing I'm worried about. Okay, I know for sure we're going to do 22 and 23. So let's start there.